Okay, in this video we're going to be looking at section 5.3, double integrals in polar coordinates. So first we'll look at how we did this in Calculus 2. Area in polar coordinates for a non-negative continuous function f on an interval, closed interval, alpha to beta, where 0 is less than beta minus alpha, which is less than or equal to 2 pi. Then the area of the region bounded by the graph of r equals f of theta between the radial lines theta equals alpha and theta equals beta is area is equal to 1/2 integral from alpha to beta r squared d theta. So we could draw an example of this. So here would be your graph of, or part of your graph of r equals f of theta. And we'll just look at something in the first quadrant, and then you have your radial lines alpha and beta. And then what we do is we partition this up into smaller sections, and then we use the area for a sector of a circle, and that's how we come up with this formula. So if we look at finding the area bounded by r equals 3 cosine of 3 theta using the Calculus 2 approach, what we're going to do first is we're going to set the 3 theta equal to the poles 0, pi over 2, pi, and 3 pi over 2, also 2 pi. That's going to give us theta is equal to 0, pi over 6, pi over 3, pi over 2, and 2 pi over 3. Okay, and then we're going to make a table. So theta and 3 cosine of 3 theta. So at 0, pi over 6, pi over 3, pi over 2, and 2 pi over 3. If we evaluate the 3 cosine of 3 theta of that, that's going to give us 3, 0, minus 3, 0, and 3. So if we sketch this, so let's get sketching, and then we'll do all in our polar coordinate system also. Okay, so we're going to go back one. We're going to go to negative pi over 6 also, and that's going to be the first petal. So this is a rose curve, or rose petal, or what my wife likes to call it, a daisy petal, because she thinks it looks more like a daisy. She's probably right. Anyways, it's called a rose curve mathematically. So we'll put out our radial lines, negative pi over 6 and pi over 6, and then 3, and then we'll do our sketch of our rose petal. So there's our first rose petal, and then this gives us induced order. Okay, now we'll do our second rose petal. Okay, so there it is. So normally we would go out pi over 3, but because of the sign is negative 3, we're going to go in the opposite direction, so it's going to come down here, okay? And then our radial lines would be, again, pi over 6 extended into quadrant 3, and pi over 2 extended, I guess, sort of into quadrant 3. It's on the boundary there. So that gives us our second petal. All right, and then finally, at our last petal, we're going to have to go a little bit further. So 2 pi over 3 is the same thing as 4 pi over 6. So add a pi over 6 and gives us 5 pi over 6. So we increase by pi's over 6. Okay, and so that gives us our last one. So the maximum there is going to be at 2 pi over 3, and it's going to fit between the radial lines of pi over 2 and 5 pi over 6. Okay, so there it is. All right, and this is symmetric, and so what we want to do is we just want to find the area of one of these petals and then multiply it by 3 to find the area of all of them. So we can find the area of any of those petals. I'm going to do the first one where our radial lines are negative pi over 6 to pi over 6. So our area is equal to 3 for the 3 petals, and then 1/2 is part of the formula. Integral from negative pi over 6 to pi over 6 of r squared, so 3 cosine of 3 theta squared d theta. So it's going to give us 27 over 2, because we're going to do the 3 squared. I'm going to pull that out times the 3 and give us 27 over 2. Integral from negative pi over 6 to pi over 6 of cosine squared of 3 theta. So again, that coefficient of 3 that was out in front when we squared it, so this right here, it's going to be a 3 squared. So I just took that out. 3 times 9 would be the 27 that you see there. Okay. Now we're going to use a power reducing formula. So the cosine squared is equal to 1 plus cosine of 2 theta over 2. So it's going to be 27 over 2. Integral from negative pi over 6 to pi over 6. And then the cosine squared of 3 theta will become 1 plus the cosine, and we double the angle, so the angle was 3 theta, so it becomes 6 theta all over 2 d theta. So this is going to be 27 over 4, because I'm going to slide that division of 2 out. Integral of 1 with respect to theta is going to be theta, plus the integral of cosine of 6 theta is going to be the sine of 6 theta divided by 6. And then we're going to evaluate that from negative pi over 6 to pi over 6. Okay? Now I don't think I write it down here, but if I plug in pi over 6, I'm going to have the sine of 6 times pi over 6, which is going to be the sine of pi, and that's going to be 0. Okay? If I plug in a negative pi over 6, I'm going to just have a negative there, and it's still going to be 0. So I don't think I even bother to write that because that part zeroes out. Okay. All right, so then we have, this is equal to 27 over 4, equal to 27 over 4, pi over 6, and then minus negative pi over 6. So that's going to be 27 over 4, and then times 2 pi over 6, and that simplifies to 9 pi over 4, and then we're finding an area, so that's going to give us a unit squared. Okay. All right, so the next slide we're going to look at, and what we have here is the coordinate conversion. So the polar coordinate r comma theta of a point the polar coordinate r comma theta of a point are related to the rectangular coordinates x comma y as follows. So your polar to rectangular, x is equal to r theta, y is equal to r sine theta. Rectangular to the polar is tangent of theta is equal to y over x, and r squared is equal to x squared plus y squared. Now, when we looked at section 2.7, we had an introduction to cylindrical and spherical coordinates, so that's coming again in chapter 5. Cylindrical coordinates are polar coordinates, but they just go into the third dimension. I believe it's the last section or the second to last section that we're going to cover in chapter 5. It has to do with something called the Jacobian. The Jacobian is going to be kind of the cost of converting from rectangular coordinates to the polar or later the cylindrical coordinates. So the Jacobian, we set up this little matrix here, and it is dx dr. So dx dr would be the cosine of theta, and then dx d theta would be negative r sine of theta. dy dr would be the sine of theta, and then dy d theta would be equal to the r cosine of theta. Well, then we take these and then we put them in a matrix, a 2 by 2 matrix, and then we take the determinant of them, and we get the r squared theta minus negative r sine squared theta, and then the Pythagorean identity will tell us that that's equal to r. That's the Jacobian, so that's going to be your price for changing your coordinate system. So the change of variables to polar coordinate form, the double integral over the region R of f of x, y, dA, where the dA could be dx, dy, or dy, dx, is equal to the integral from alpha to beta, integral from g1 of theta to g2 of theta, f of r cosine of theta, comma r sine of theta. So you take your function f of x, y, and replace the x with r cosine of theta, and the y with r sine of theta. And then you got the r right there. So if you see that r right there, that's your Jacobian. If I can spell Jacobian, it's right in front of me. That's your Jacobian, and then we integrate dr d theta. Okay. So I think it's probably not the next example, maybe a little bit later, that we'll do something that's in rectangular coordinate system and we'll convert it to polar. And then we'll do that quite a bit in I think it's 5.5 or 5.6 of this chapter. Okay, so let's go ahead and go back and look at that same problem. So I'm just going to re-sketch. And so we have the area is equal to 1/2 negative pi over 6 to pi over 6. And this is just going to be the area of one petal. 3 cosine of 3 theta squared d theta. And so I'm going to make the claim. That this is going to be equal to the integral from theta equals negative pi over 6 to theta is equal to pi over 6. Integral r equals 0 to r equals 3 cosine of 3 theta r dr d theta. So I'm going to say that this is the same thing. So when I integrate that, I get the integral from negative pi over 6 to pi over 6 of 1/2 r squared, and then we're going to evaluate that from 0 to 3 cosine of 3 theta d theta. And so that's going to be equal to the integral from negative pi over 6 to pi over 6 of, and then we can slide the 1/2 out, and then it would be 3 cosine 3 theta quantity squared, and then minus 0 squared, which we don't need to include. And so if we start with this here, it in fact is equal to the same integral that we had before, and so we can represent these regions areas as double integrals as opposed to single integrals like we did in Cal 2. So I think we're going to work on one more of just strictly polar, and then we're going to look at 2 examples where we're given something in the rectangular coordinate system, and then we'll convert it to the polar coordinates. That'll make it a little bit easier. So let's go to our next example here. So we're going to find the area bounded by r equals 3 minus 2 sine of theta. There's no constant multiplier of the theta, so we just use our standard poles, angles. So that'd be 0, pi over 2, pi, 3 pi over 2, and then 2 pi. Okay, so if I evaluate this at 0, the sine of 0 is 0, so we have 3. Evaluated at pi over 2, the sine of pi over 2 is 1, so we have 3 minus 2 is 1. Sine of pi is 0, so we're just left with 3. The sine of 3 pi over 2 would be negative 1, so we have 3 minus 2 times negative 1, so that becomes 5, and then the sine of 2 pi is 0. So it gives us those points. Okay, and then we're just going to graph this in how we would have done this in like a pre-calculus class. Okay, just on a regular XY plane. Okay. So what we have with our sine function is a vertical, well, it's a reflection over the x-axis, then a vertical stretch by 2, and then shifted up 3 units. Okay. All right, so let's go ahead and erase some of this so we can draw a rough sketch of this in the polar coordinate system. Okay, so we're going to start out at 3 on the east axis. On the north axis, we're going to be at 1. The west axis, we're going to be at 3 again. That's the distance from the pole. And then 3 pi over 2, we're going to be all the way out at 5. Okay, and so we'll just try to sketch what we got going on. So it's going to be fairly flat at 1, so we're going to have a little bit of a dimple at 1. Okay, and then there it is. So mine kind of looks like an apple, or maybe a little bit of a deformed heart, or something like that. It's probably going to be a little bit rounder if you use something like Desmos to sketch it. So for what I'm doing, my sketch is good enough here. And it doesn't repeat itself or anything. I guess one thing you could do is you could just, it is symmetric, so you could find the area of half of it. I'm just going to find the area of the whole thing. And by find the area of half of it, I mean find the area of half of it and double it. Anyways, so we're going to do an area, and we're going to find it using double integral. So I'm going to go from 0 to 2 pi. That's how long it takes for this thing to repeat itself. And then we're going to do integral from 0 to the r function, which is 3 minus 2 sine of theta. And then we have r dr d theta. And then we're going to go ahead and integrate that. So it's the integral from 0 to 2 pi of r squared over 2, evaluated from 0 to 3 minus 2 sine of theta, d theta. So we can slide the factor of 1/2 out. So we have the integral from 0 to 2 pi of 3 minus 2 sine of theta quantity squared d theta. So it's going to give us 1/2 integral from 0 to 2 pi of 9 minus 12 sine of theta minus 4 sine squared of theta d theta. Move some of this out of our way. Okay, and then we're going to make a note. Power reducing formula, sine squared of theta is going to be equal to 1 minus cosine of 2 theta all over 2. So we're going to make that replacement. So our integral becomes the integral from 0 to 2, 9 minus 12 sine of theta minus, we have a mistake, that's why. This should have been a positive here, because we have negative 2 sine of theta times itself, so that should have been positive there. Okay, so plus 4 and then 1 minus cosine of 2 theta all over 2, and then d theta. So it's going to be 1/2 integral from 0 to 2 pi of 11. So the 11 came from the 9, and then we have 1/2 times 4, so that'd be 2. So 9 plus 2 would be our 11. Minus 12 sine of theta, and then minus 2 cosine of 2 theta, d theta. So that's going to be 1/2 integral, we already integrated. 1/2 and then 11 theta plus 12 cosine of theta minus 2 sine of 2 theta all over 2, and then we're going to evaluate that from 0 to 2 pi. So it's going to be 1/2 11 times 2 pi, and that's going to be 11 pi units squared. The rest of it is not going to matter, but I'll show you why. So if we look at the cosine, we have 12 cosine of 2 pi minus 12 cosine of 0. So both cosine of 2 pi and 0 are 1, so it gives us 12 minus 12, which is 0. So that doesn't matter. And then if you plug in 2 pi into the sine, you're going to have the sine of 4 pi, and sine of any integer multiple of pi is going to be 0. Likewise, if we plug 0 in, the sine of 0 is 0. So those didn't matter there. Okay, so we got our units of 11 pi squared. All right, let's go on to the next slide. So possibly in Calculus 2, you went through the Wallace's formulas. You would use some integration by parts and some formulas for integrating cosine to the second power, third power. We kind of look at some patterns here. Anyways, so Wallace's formulas, if n is odd and greater than 3, then the integral from 0 to pi over 2 of cosine to the nth power x dx is going to be the same as the integral from 0 to pi over 2 sine to the n power x dx, which is going to be equal to 2/3, 4/5, 6/7, all the way out to n minus 1 over n. If n is even and greater than 2, then the integral from 0 to pi over 2 of cosine n to the nth power x dx is equal to the integral from 0 to pi over 2 sine to the nth power of x dx, and that's going to be equal to 1/2 times 3/4 times 5/6 ... all the way out to n minus 1 over n, and then times pi over 2. So that's going to come into play in this problem just to facilitate some integration that will be a little bit tedious. So first thing we're going to do is we're going to sketch the region that we have. So the y is going to go from 0 to 4, and the x is going to be equal to 4y minus y squared under the square root. Square both sides, it's going to be x squared is equal to 4y minus y squared. So x squared plus y squared minus 4y is equal to 0. So x squared plus y squared minus 4y plus 4 equals 4. So we're going to complete the square. So we have x squared plus y minus 2 squared is equal to 4, or 2 squared. So what that is a circle centered at 0, 2 of radius 2. So we'll go ahead and attempt to sketch that. So there's your circle, and that's the region that we are finding. Well, we're actually finding the area, not the area, we're finding the volume underneath z equals x squared in this, above this region right here. That's what we could think of this integral representing. Okay. So what we want to do is we want to convert this into polar coordinates. Anything with a circle like this is going to be easier to do in polar coordinates. So we got 0 to pi over 2, and that's going to be our limits of integration for converting this into polar coordinates. Now, we're going to take x squared. Remember, x is equal to r cosine of theta, so we have r cosine of theta squared. Y is r sine of theta, minus 2 quantity squared, and that's going to be equal to 2 squared. So this is going to give us r squared cosine squared theta plus r squared sine squared theta minus 4r sine of theta plus 4, and that's going to be equal to 4. The 4's will absorb. R squared cosine squared plus r squared sine squared, using the Pythagorean theorem, not the Pythagorean identity, that'll just be r squared, because cosine squared plus sine squared is 1. Okay, minus 4 r sine of theta. That's going to be equal to 0. So we can add 4 r sine of theta to both sides. And then divide by r, and so r is equal to 4 sine of theta, and that describes the circle there. So then our radius is going to go from 0 to 4 sine of theta. X is equal to r cosine of theta, so we have r cosine of theta squared. Don't forget the Jacobian, so that's the price to convert to this coordinate system. And then we have dr d theta. So that's going to give us the integral from 0 to pi over 2, integral from 0 to 4 sine of theta, and then we're going to have r to the third power cosine squared of theta dr d theta, which is equal to the integral from 0 to pi over 2 of r to the fourth over 4 cosine squared of theta, evaluated from 0 to 4 sine of theta d theta. So slide the 1, well, I guess I didn't slide the 1/4 out. So it's going to be equal to the integral from 0 to pi over 2 of 4 sine of theta to the fourth power over 4 cosine squared theta d theta. Okay, I think this is what I did. So 4 to the fourth over 4 would be 4 to the third, which is 64. Integral from 0 to pi over 2, okay? And this is a trigonometric integral here, and because we got the Wallace's formulas here, I think we're going to use the Wallace's formula. And then here's that Pythagorean identity I used earlier. So sine squared of theta plus cosine squared of theta is equal to 1. So if you multiply that by r squared, you'd have that part right there, and then that would just turn into r squared. I'm going to use that and solve that for cosine squared, and so I'd have cosine squared is equal to 1 minus sine squared. So we're going to make that replacement. So you have sine to the fourth theta, and then 1 minus the sine squared of theta d theta, and that's going to be equal to 64. And then integral from 0 to pi over 2 of the sine to the fourth of theta d theta, minus the integral from 0 to pi over 2 of the sine to the sixth power of theta d theta. Let's move some of this out of our way. Okay, and now we're ready to use the Wallace's formula. Both the exponents are 4 and 6, so by both I mean they're both even. Okay, so the first one is going to go to n, which is 4, so 1/2, 3/4, and then pi over 2. So that's going to be 64 times 1/2, 3/4, and then pi over 2. and minus the second one. So the exponent there is a 6. And so we're going to go 1/2, 3/4, 5/6, and pi over 2. So 1/2, 3/4. Your n is 6, so that's where we're going to stop. 5 over 6 times pi over 2. Okay, so there's going to be 64. We're going to factor out a 1/2, a 3/4, and a pi over 2. What remains is a 1 minus a 5/6. Okay, so then we're going to have, after we simplify, 12 pi times 1/6. Okay, so our area here is going to be 2 pi square units, and it's not squared because we're doing this as a volume underneath x squared, so this should be a cubed here. Okay. All right, hang in there. We got one more problem for you. One more. Okay. So this one here, it says to rewrite as a single double integral by converting to polar coordinates. So we have the integral from 0 to 5 root 2 over 2, integral from 0 to x of xy dy dx, and then we have plus the integral from 5 root 2 over 2 to 5, integral from 0 to the square root of 25 minus x squared of xy dy dx. All right, so the first integral is x is equal to 0 to x is equal to 5, root 2 over 2. Y is equal to 0 to y is equal to x. Those are the limits of integration for the first one. In the second one, we have x is equal to 5 root 2 over 2 to 5. And then limits of integration for y are y equals 0 to y equals the square root of 25 minus x squared. So we're just going to put all this information in and kind of see what we're looking at here. Square both sides, and we have y squared is equal to 25 minus x squared. So this looks like we're looking at a circle. X squared plus y squared is equal to 25 squared. So let's go ahead and sketch it. So x and y are equal to 0. X is equal to 5 root 2 over 2. So that's going to kind of point us to being in quadrant 1. So we'll go all the way out to 5. So we got a circle of radius 5. Okay. And then the first integral, the y is going from 0 to the square root of to just x, so that's your identity right there, and that intersection there is going to be 5 root 2 over 2, and so that's what the first integral represents, is that area right there. The second integral does the rest from 5 root 2 over 2 to 5, and then the upper function is the square root of 25 minus x squared. That's the circle. Okay, so can we put this together and just have one integral? So we would need to find what this angle is right here, and then we just have a nice circle. Okay, so we got the hypotenuse here is going to be 5. That's the radius, and we know that the base is 5 root 2 over 2. So we can use the cosine of theta, which is going to be equal to the adjacent 5 root 2 over 2 divided by the hypotenuse of 5. So the cosine of theta is equal to root 2 over 2. So that's going to occur when the theta is equal to 45 degrees, or pi over 4. So we're going to go from 0 to pi over 4. So 0 to pi over 4. And then a radius is easy. It's just 0 to 5. Okay. Now we got to convert the integrand, the xy, into polar coordinates. So the x would be r cosine of theta, and the y would be r sine of theta. And don't forget, we got to pay the price to change the coordinates. So you got your Jacobian of r, and then dr d theta. So we got this integral from 0 to pi over 4, integral from 0 to 5 of r cubed sine of theta cosine theta dr d theta. So that's going to be equal to the integral from 0 to pi over 4 of r to the 4th over 4, and then u is sine and du is going to be cosine. Is going to be the substitution we do in a minute here. Evaluate from 0 to 5 of and then integrate with respect to theta. So r to the fourth, 5 to the fourth is 625 over 4. Slide that out. Integral from 0 to pi over 4. Sine of theta, cosine of theta, d theta. So that's going to be 625 over 4. Sine squared of 2. Sine squared of theta over 2. And then we're going to evaluate that from 0 to pi over 4. This is going to be 625 over 4. Oh, okay, so I guess I multiplied the 4 and the 2. Okay, so over 8. And then sine squared of pi over 4. Pi over 4 is root 2 over 2. So root 2 over 2 squared. Okay, and then sine of 0 is 0, so 0 squared. So 625 over 8. And then root 2 over 2 squared is going to be half. And so that's going to give us 625 over 16. And that should be units cubed because we're doing we got a height function, the x, y, so I should say cubed there. Okay. Alrighty, well, that's it for this section. So we've got the first 3 sections of Chapter 5 done, and then stay tuned to next week for the next parts of Chapter 5.